this is a review of what you went over in Physics 20 as far as systems and work and energy goes. Although I guess we didn't really define systems so much in Physics 20, that's more Science 10, but let's just quickly go over, make sure you remember what all the different types of systems there can be. Of course, we can have an open system where you can exchange both matter and energy with surroundings. External forces can act. Mechanical energy isn't conserved, but overall energy is. This is, of course, the world we live in quite often. And then we have a closed system, which is a system that can exchange energy but not matter, which is really important. And then it's not subjected to external forces. So this is a situation that we often look at in physics, where it's really part of a bigger system that is open, but then we close it by just considering, the time of a ball dropping from when it's dropped to the millisecond before it hits the ground. And if that's the system, then there's an exchange of energy, but there's no exchange of matter. There's no external force. We know as soon as the ball hits the floor, there will be an external force at the floor on the ball. But if we consider the system up until the moment, the millisecond before it hits the ground, then there's no external forces. There's just gravity, and we can call that a closed system. So that's often what we do in physics in order to look at things as closed systems. As a bigger system, they are definitely part of an open system, but we can usually with time, we just look at a certain time, and then within that time, we have a closed system. So that's often how we get away with that in physics. And of course, there's isolated systems, which isn't something we deal with a ton, but that's where neither matter or energy can be exchanged. No external forces, no energy lost to heat, and no energy gained from applied forces. So again, that often does not happen. Typically in physics, we want to look at closed systems. All right, so let's talk a little bit more about work and energy and what you learned in Physics 20 and what's really important that you bring over into Physics 30 again. So remember, work is the ability to move an object through a distance, and that distance has to be parallel to the force being applied, okay? It is a scalar, which is really, really nice because sometimes we're working with vectors, and therefore we have to take direction into account. And sometimes if we can look at things in terms of energy or work, then we don't have to consider vectors, which is actually something that comes into play in momentum, because momentum is a vector, or sometimes we need to use conservation of momentum, but sometimes we can look at the exact same thing with conservation of energy instead, and then we don't have to worry about directions, which is really nice. Okay, so remember, we find work by doing FD times cos theta. That angle is the angle being made with the displacement, right? The force makes with the displacement, because we only want the component of the force that is parallel to the displacement. That's the only thing that is doing work. And then we have energy, which is just the ability to do work, also another scalar. So you can categorize it, of course, as either potential or kinetic. Potential is stored energy. Kinetic energy is the energy of motion. Here's the three we went over in Physics 20, gravitational potential, mgh, kinetic, 1/2 mv squared, and elastic potential energy. That's when you have a spring or an elastic or anything like that, 1/2 kx squared, x being the displacement from equilibrium. Okay, so let's talk about mechanical energy, which is, of course, the sum of potential and kinetic energy. It remains constant in an ideal isolated system, which, like I said, we don't really deal with a lot. Every once in a while we will, and we'll assume isolated system, and that's when we have only conservative forces. And so we know mechanical energy before is equal to the mechanical energy after, so the sum of energies initially is equal to the sum of energies finally. So you consider your initial position, what kind of energies do you have? Consider your final position, what kind of energies do you have there? And the sum of all those energies should equal the same number before and after. Okay, so that was conservation of energy, the law of conservation of energy, which is principle 5 on your data sheet. And that is if no heat is lost to friction. or no energy is lost to heat like friction. So, of course, we know mechanical energy is not conserved if the system is not isolated. If you have an open system or even just a closed system, which again is what we often have in physics 20 and 30. And so external work is done because there's work being done, if we're in the case of friction, by the ground on whatever is moving across the ground. And so that's this thermal energy is lost due to friction. That would be air resistance as well. A lot of ways to lose energy due to friction, due to heat. And so for that, since it's a little bit different, since we now don't have conserved energy, we need to use the work energy principle, which is that work done is equal to the change in energy, because we know that there's a change in energy when there is thermal energy lost due to friction. Okay? Now remember, this was able to be extended into a really, really, really big equation, because work, well, you have your work done by an applied force, but that thermal energy is also doing work. So this work right here should actually be broken up into two things. And then, of course, change in energy. Well, we have three types of mechanical energy that could be changed. And so we have the work done by our applied force plus the work done by our thermal force should equal to the change in energies of all of them, the sum of all those. And of course, then we expand that into an even crazier equation, because we know work is equal to FD times cosine theta. And then we have all the equations for our kinetic, gravitational potential, and spring potential energy. So it goes into this insane thing. Hopefully you remember this from physics 20. But the good news here is that we will assume that this guy is the cosine of 0. Oops, I just drew another theta. Didn't mean to do that. Cosine of 0 is 1. So this, we can just kind of get rid of that. Friction is always, always, always at a 180-degree angle. Cosine of 180 degrees is -1, so this, you can get rid of that and just turn that into a minus. Okay? And so that turns into that, which is still actually longer, because then I took all these equations and actually broke it down at their equations. But of course, we won't ever have a situation where we're like going to consider the initial position where it has initial kinetic and gravitational potential and spring potential, and where finally it has finally it has kinetic and gravitational potential and spring potential. That is not a situation we're ever going to look at, right? So even though this looks insane right now, it gets better. Okay, so remember in physics 20, I broke this down a little bit more. I rearranged in just a way that helps me remember a little bit better. And that's the work done by the applied force. So force times of the applied force times displacement, plus all my initial energies is equal to all my final energies, plus work done by the frictional force. Okay? So if you remember that, keep that in mind. That'll help you out a lot. Okay? And so then anytime we want to know what's the change in energy, or energy happens, or what energy conservation is happening or energy transfer is happening, but we know friction's there, we can use this equation. Okay? Now, of course, like I said, always choose a specific initial position and final, so you don't have all three energies at both positions, because that'd be crazy. That'd be insane. So let's do an example using what we know about all this fun stuff about work and energy. And again, this is fully 100% just review from physics 20. Okay, so we have a 90-kilogram crate starting from rest. Always nice to know. So we know initially it doesn't have any kinetic energy. It's pulled across the floor with a constant horizontal force of 350 newtons. So constant horizontal force just means it's continually being pushed, right? Sometimes we have something being pushed, and then when it's no longer being pushed, it's therefore no longer has an applied force, okay? So it's no longer, this one is being constantly pushed across the floor. For the first 15 meters, the floor is frictionless. How nice. And for the next 15 meters, the coefficient of friction is 0.30. What is the final speed of the crate? So I'm guessing that's at like the second 15-meter mark. So what the heck is going on? Diagrams are always nice, aren't they? So we're going to draw our diagram of this crate being dragged across the floor. Okay. And so we know that we kind of have two portions here. We have 15 meters right here where we have no friction. So that means our coefficient of friction is 0 and friction is just 0 in general. And then we know we have these second 15 meters where we have a coefficient of friction of 0.30. And so we're trying to find the velocity at this point. Okay, so we know the velocity at this point is 0. So I kind of have three main points here, right? I have the beginning, the middle, and the end. And why we have to consider the middle is because we know that for the first 15 meters, none of this force is being lost to thermal energy, right? None of the force being put in, the 350 newtons, is being lost to thermal energy, but I know the second 15 meters, there is, okay? And so I actually kind of need to separate these two and think of the first 15 meters as one situation, the second 15 meters as another. So I'm going to call this guy position 1, this guy position 2, and this guy position 3, just because it kind of helps you, because right now initial and final isn't going to help us, because in the first bit, initial will be 1 and final will be 2, and then 2 will become initial and 3 will be final. So sometimes initial and final, there's limits to that, and it's just better to label your positions 1, 2, 3, or A, B, C. Okay, so I'm going to call the velocity at 1, 0. I should probably find the velocity at this point, at point 2, so I know how much speed it gains while it's on the frictionless surface, and then I'll have the friction surface to be able to find the speed at point 3, its final speed. Okay, so I'm basically considering these two separate situations. So again, from here to here, that's going to be one thing, and then from, let's use pink. From here to here is going to be a whole different situation. Okay, so first I'm going to go over the frictionless thing and figure out what this final speed would be there, and then I'll go over the surface with friction and what the speed would be and how much of that speed will be lost to friction. Because obviously it's going to gain a lot of speed from 1 to 2, and it's still going to gain speed from 2 to 3, but I don't think as much, right? Because some of that is lost to friction. Okay, frictionless portion, let's look at that. And that was our yellow bit, so I'll highlight that in yellow. Okay, so frictionless. When we look at this, now of course, you never need to actually look at this whole crazy, never have to write that all down, but let's just write it all down really quickly. So again, we can see just how much actually cancels out when we're looking at this. So remember, work done by the applied force. So applied force times displacement plus all my initial energies, mv squared, so that's mv1, plus mgh, plus 1/2 kx squared is equal to all my final energies, so 1/2 mv, and of course that's going to be at position 2, plus gravitational potential, plus spring potential, plus work done by friction. Now, we can get rid of a ton of these because, first of all, we know there's no gravitational potential energy or spring potential energy anywhere. So these all cancel out. Those both cancel out. Don't need to worry about them. Is there kinetic energy at point 1? No, it's starting from rest. It's not moving, so we don't actually have any kinetic energy at point 1. Do we have kinetic energy at point 2? Absolutely we do. Do we have any work done by friction here. No, it's literally the frictionless part of this. So really, what do we have? We actually do have just our work is equal to change in energy. But that's why if you remember this equation for basically anything that has to do with work, and energy, then it's gonna serve you well, because it's basically just an extension of everything you've done in work and energy. So we end up with the fact that work is equal to, guess what? The change in energy. Oh, imagine that. So that is, of course, our applied force times displacement should equal to 1/2 mv squared. We are looking for the speed at point 2, so I'm going to solve for that. So I should get 2 times the applied force times displacement divided by the mass, and square root that, and then we can plug our numbers in. And for our speed at point 2, therefore we get 10.8 meters per second. Okay, so that's the speed right here is equal to 10.8 meters per second. Perfect, and now that can help us find the final speed, which will be the speed at point 3 after it's gone the 15 meters with the force of friction. Okay, and so that's what we're gonna do now. We're gonna go over the friction surface, okay? Well, the pink looks so pretty. Okay, so when we look at this crazy equation again here, I already wrote it up here, so I'm not gonna write it out again. But now we can kind of go through and pick and choose what we have. And again, now position 1 is, the initial position is position 2, and then the final position is position 3. So of course we still have that applied force, so I'm going to keep that there. And then we do have kinetic energy at position 2. Okay, but it's still no gravitational potential or spring potential. So that's it for your applied force and initial energies. And then that should be equal to all your final energies, which again is just kinetic. We really have no gravitational potential or spring potential energy happening here. So that's a 3, by the way. It looks like a B, but it's speed at position 3. And then of course here we do have friction. Now, here's a question. We need force of friction. How do we find force of friction? So, going back to physics 20, we probably should remember the fact that force of friction is equal to mu Fn. And then we need to figure out what the heck Fn is. So if you do not remember, then, well, you better pay attention. We find out Fn by using Newton's second law. The sum of the forces is equal to mass times acceleration. How do we get the sum of the forces? Well, it's probably a good idea to draw a free body diagram. So what's a free body diagram again? Oh, right, it's one of these things where you draw all the different forces at work on this thing. So we have normal force, we have gravitational force, we have an applied force at this point. And of course, at position 2, we will have a frictional force going in the other direction. But if I want the normal force, then I'm just looking at the sum of forces in the y direction, because normal force is in the y direction. Okay, so if you remember that, we'll say upwards is positive. We say all the sum of the forces in the y direction is equal to mass times acceleration in the y direction. It's not moving in the y direction. That is 0. Okay? And so, of course, sum of forces, well, that's normal forces upwards minus gravitational force, which is downwards, is 0, which means Fn is equal to gravitational force, which is, of course, mg. So, when I look at the fact that frictional force is mu times Fn and Fn is mg, guess what I can do here? I can substitute that in for my force of friction. So this changes a little bit. None of this changes, so just rewrite all this. But this force of friction becomes mu mg, and then of course times displacement. Don't forget that times displacement. A lot of people tend to. Okay, what the heck are we looking for again? Oh, right, the speed at position 3. I think I have everything else here. I've applied force, I have displacement, I have mass, I have the speed at position 2 because we found it. I have mass again, and mu, and mass again, and g, and displacement again. Okay, I got everything except for the speed at position 3, which is what I'm going to find right now. And I'm going to rearrange this equation to get this. Okay, and then what do we got to do? We have to plug in those numbers. Hopefully I will have enough room. I got to write really, really tiny. And we shall see if I can fit this all in this little line here. Just a reminder, I am a stickler for accurate values. So remember, here I just wrote 10.8, there. I'm not actually, when I plug this into my calculator, not using 10.8. I'm using the previous answer on my calculator, okay? Another thing to be careful here, make sure this 2 is being multiplied by everything inside the brackets, okay? So that comes from when I first subtract this mu mgd from both sides. So it goes over there, and then I multiply both sides by 2 to get rid of this 1/2. And so that means I need to multiply everything on that side by 2. So this 2 should apply to like everything in there, okay? So just keep that in mind. And yeah, and if you put this in your calculator correctly, you should get 12 meters per second, okay? And I did put it as 2 significant digits because I had 2 here and 2 here. I had 3 there, but, you know, and 2 here and 2 here. So I used 2 mostly significant digits, so my answer should be 2 significant digits. And so, yes, we're getting back into the world of having to remember all that. So lots to keep in mind when you're going over this sort of thing. But that still fully is a Physics 20 question. And that is something that you did in Physics 20. So this is really just a reminder here because it's going to come into play in momentum. So hopefully that helped, and hopefully it's coming back to you pretty quick.